Hi everyone, welcome back to Physics 142, your course on electricity and magnetism. And we're approaching the end here, so keep hanging in there. We're getting really close. So I just want to briefly talk about where we've been and where we're going. So we have spent a long time first dealing with electricity, and what we realized is that charges produce electric fields, and we had a couple of equations that sort of told us things about charges producing electric fields. So we had Coulomb's law, right, which said add up all the dq's, add up all the q's, look how far away you are, that gives you some electric field. We had Gauss's law, which told us that charges produce electric flux. So that was the first part of electricity and magnetism. And then we have now been dealing with magnetic fields. And we've realized the way that you get a magnetic field is with current, right? With moving charges. So just having a charge gives you an electric field. If you set that charge in motion, then you get a magnetic field. So we realized that if you have current that is moving charges, right, that gives you magnetic field. This was the Biot-Savart law. And then more recently, we had Ampere's law, which said that, again, if you enclosed current in some sort of loop, that gave you magnetic field. So again, current or moving charges gives you magnetic field. Now, another cool thing that we realized in the last few videos is we realized that while we can make electric fields with charges, it turns out there's actually another way to make electric fields, or we could say another way of making current. And what we realized is that if you change the magnetic field, and more specifically, we realized if you change the flux, right? If you change the magnetic flux, then what you get from changing the magnetic flux is you get an induced EMF, or we talk about an induced current, right? An induced potential and an induced current. So just like current creates magnetic fields, if you change a magnetic field, you can get current. And we most recently realized that the way that you're getting this current is actually by making an electric field. So if you change the flux, change the magnetic flux, you actually create this non-conservative electric field, this looping electric field. And that ends up, it's this non-conservative electric field, which ends up actually providing the force that makes this current flow in the first place. And that is really exciting. Changing magnetic flux actually is another way of making an electric field. I could take this formula, actually maybe put it down here, right? We have a new way of making an electric field. Just as a brief aside, something I should mention kind of from the end of class last time, I posted an extra video about this, but just wanted to note that these non-conservative electric fields tend to go in sort of circles, right? And so if you do this, if you change magnetic fields in 3D, you end up getting these swirling currents, right? These sort of circular currents. So, imagine having some metal disc, you get swirling currents in that if you change magnetic fields across a big disc, and those are called eddy currents. And so I encourage you to watch the video. It's not something we're going to go into detail in this class, but it's pretty interesting if you're interested in things like magnetic braking. This is the way that we do it, by inducing these currents in 3D materials, these eddy currents. So that hopefully gives you just a little bit of a picture about where we've been, right? We're sort of, deep in the middle of magnetic field stuff right now, right? Dealing with this magnetic flux, but I think it's also useful to step back, and we will do more of that at the end of this week. So with all of this in mind, I now want to ask a question that maybe this has sort of come up to you, or bothers you a little bit, is we've talked about the fact that when you change magnetic flux, it induces current, and specifically that current or that potential is always resisting the change, right? It's always opposed to the change, and we put that in with this little minus sign. And so that actually brings us to an interesting question of, is this opposition to change, does that ever impact sort of the current or the circuit that's actually making the magnetic field in the first place? And that is this idea of self-inductance. And so to see that, let's draw a couple of circuits and sort of think about how they're different, all right? So one circuit I want to draw here is, let's just draw a circuit that is just a power supply and a resistor, all right? And we'll have some current run through this circuit, all right? We'll have current run through this circuit, and it'll just be a constant amount of current, all right? And there are a couple questions I want to ask, all right? The first question I want to ask is there a B field created? All right, do you get a magnetic field in this case if you just have constant current? Well, think about that. So hopefully you voted, all right? My vote is that if you have current, then you get a B field, all right? And specifically, this field would be into the page, right? You can wrap your fingers in the direction of the current, right? That's going to create a magnetic field that's into the page, and so we will get a magnetic field that's into the page from this circuit, all right? Now, another question that I have then is there going to be any induced current? All right. So we know that just, this power supply creates a current, which creates a magnetic field. But sort of a question is, what about induced current? All right. So, induced current, question mark. So, here the answer was yes, all right? And induced current, well, to ask a question about induced current means we're asking about a question of, is the magnetic field changing, right? We need to have changing magnetic field to induce current. And here, if the current is steady, right, if we have steady current going around, we have a constant magnetic field, and so there's not going to be any induced current, all right? So, no, unfortunately. All right, so that's all well and good, all right? But now let's contrast this with another circuit, all right? Well, actually the same circuit, but now we want to put a switch in it, all right? So let's put a switch in this circuit, all right? So here's, my resistor again, my power supply, okay? And I want to ask the same questions, all right, let's think about right after I close the switch, all right? After I close the switch, all right, let's ask the same questions. Will there be a B field? All right, well, that's the first question. Will there be a B field? Well, as soon as we close the switch, we're going to start getting some current flowing, right? We'll start getting current flowing, and that will look a lot like this circuit. And so, yes, we will get a B field, right? Once we close the switch, we'll get some current flowing, and we'll get a B field, at least a little bit, right? So, will there be a B field? Yes, there will. Okay. Is that B field changing, and will there be an induced current? Well, so is B changing? Well, right after we close the switch, you betcha, right? So right after you close the switch, the current, it's going from zero current to some current, so clearly the current is changing, and if the current is changing, that means the magnetic field is changing, all right? So if the magnetic field is changing, okay? But if the magnetic field is changing, that means you better be inducing some current, right? If you are changing the magnetic field, that's going to induce an EMF, right? That will induce some current. So induced current. All right, now the answer to that is yes. All right, yes, you're going to induce some current here. All right, and well, what direction is that induced current? Well, remember that the induced current always opposes the change, right? So we have increasing magnetic field here, increasing into the page. So if the change is into the page, right? So, delta B is into the page. So that means that my induced current my induced field must be out of the page, right? So B induced must be coming out of the page in here, right? It'll be coming out of the page. And if it's out of the page, that means your induced current will flow the opposite way, right? Your induced current is going to flow the opposite way, all right? So that's an interesting thing, right? We have an induced current, and it opposes the change, right? And so that means it's actually opposing the flow that created it, right? Opposes the flow that created it, all right? So, this is sort of an interesting phenomenon, right? Because now, we're trying to get some current flowing, right? We're trying to get some current flowing, but just the fact that we're ramping up that current, that we're increasing the current, means that there's going to be some opposition to it, all right? And so this actually has a name, all right? And we call this either self-inductance, right? It's we're inducing a current on sort of itself, right? So the current, the circuit that is making the magnetic field is also having an induced effect, all right? We also sometimes call this opposing EMF a back EMF, all right? So let's write this down. I need just a little more room here, all right? And we're gonna write a definition, all right? And the definition I want to do is we're gonna say back EMF. All right, back EMF is just going to be EMF, or EMF, remember, is another word for potential, right? Potential that opposes the change in current or flux, all right? So it's EMF that's opposing the change, all right? And sort of the effect of this, all right, the important effect is that it takes time, all right, before circuits reach their final value. All right, so what does this mean? All right, well, right after you close the switch, you're getting, it takes some time to sort of ramp up to getting to look like this circuit, right? Basically, what's happening with the back EMF is if we make a plot, all right, of time versus current, all right? If we make a plot of time versus current, you might think right when I close the switch, before I close the switch, I have 0 current, right? And you might think, okay, I close the switch and boom, I'm up to full current, right? That was sort of our model of current before, all right? But what this says is that, well, actually we have some opposition to getting that current going, right? When I close the switch, all right, it's not going to jump right up here to its top level, all right? It's actually going to have some opposition, and so that means that it actually takes some time. All right, so you actually need some time to get up to your full current level, and the fact that it takes time to get up to the full current level, that opposition comes from this back EMF. All right, so let's just note here, all right, takes some time. All right, and this applies to all real circuits, all right? All real circuits have at least a small amount of back EMF. It takes them at least a little bit of time to get up to their full amount of current. Now, I should mention that, this sort of brings up a question, all right? What sort of circuits, all right, are going to have more self-inductance or more back EMF? All right, let's say I wanted to increase the amount of back EMF. All right, I wanted to make it take even more time. What would I do? Well, the amount of back EMF depends on the flux, right? The EMF, the back EMF, maybe I should write this in red because that's sort of the formula, right? The back EMF or the induced EMF depends on the change in the flux, right? dB dt, okay? So we need to make, if we want to have it take some more time, if we want more back EMF, that means that we need more change in flux, right? We need to increase the change in flux, all right, that would give us more back EMF. And here's the thing for a given circuit, all right, for a given circuit, all right, the amount of magnetic field, well, that ultimately just depends on the power supply and the resistor, kind of how much current you're going to get going, right? So the way you really want to do this is remember that flux, right? Flux is B dot dA, right? If you can't really get more magnetic field, you only get a certain amount of current, right? You only get a certain amount of current. So the way you want to do this means you actually want to increase the area, all right? And usually that means using a coil with a large number of loops, all right? So to do this, in practice for a given circuit, all right, for a given amount of current, that means I want to increase the area. All right, I want to increase the area in this flux here. And so usually that means, all right, if we want to do this, we want to use a coil. All right, a coil with many turns. All right. So if you wanted to actually make this happen, if you wanted to increase the self-inductance of a circuit, you want to increase the area, and that would mean trying to, take your wire and wrap it, with many turns in it, right? Make it enclose, not just go around once, but make it enclose lots and lots and lots of area, all right? And there actually are good reasons to do this in a circuit sometimes, all right? Sometimes you don't want your circuit to change rapidly. Sometimes you don't want to go from no current to lots of current really quickly, all right? And so that means that people have actually designed circuit elements that do this, all right? And these circuit elements get a special name. They're called inductors. All right, and so that will be the topic of the next video, are these inductors, which are things that are designed to create some back EMF, to increase back EMF. So we'll do that in the next video.